Okay, so we left things off yesterday right after proving the correctness of the closure conversion translation that we covered. And so today I'd like to talk about how we go about doing a proof of full abstraction. How do we prove that when two terms are contextually equivalent in the source, that their translations are contextually equivalent in the target? Okay, so I've put some of the relevant, definitions, syntax, etc., up on the board. Hopefully, most of the stuff that we need to use. So there's the target language up there. I did not write up the source. And I've put down the definition of contextual equivalence for the target. We had the definition of contextual equivalence for the source essentially up on the board at the beginning yesterday. But they're very similar, except for the fact that for the target language, we have an extra environment delta. So just to read through it again, two target language components are equivalent in the target language, contextually equivalent in the target language T, if given some well-typed source context that has a whole of type delta gamma tau, right, which is what these components are typed under, we get back, after we plug in the whole, we get back a closed program that returns an integer. Then if we plug that context with ET1 or ET2, in both cases we get exactly the same answer when we run the program. And this is a terminating language, so we have to actually look at the integer that comes out and make sure that both of them are returning exactly the same answer. All right, so that's contextual equivalence for the target. And for the source, it's the same thing except erase the deltas, right? Okay, so the type translation is up here again. So let's get started. What do we want to prove? So this is, so remember, full abstraction says that if two things are contextually equivalent in the source, then we want to show that their translations, I'll write ET1, ET2, assuming this is what our closure conversion translation produces, are contextually equivalent to the target. So this direction is equivalence preservation, and the opposite direction, this way, would be equivalence reflection. And if we have both, then we have a fully abstract compiler. Okay? So let's focus on proving, for our translation, proving that we have equivalence preservation. That's the direction that's going to be really hard. Equivalence reflection should essentially follow as a corollary of the compiler correctness proof that we did yesterday. I won't go into that, but I'm happy to discuss it later. Okay, so here's what we want to prove, but let's sort of make this more formal. I haven't put any types or type environments up there yet. So really what we're doing is a translation. Given some gamma s, we are taking our ES1 and ES2, I'll just write ESI, right, for 1 and 2, that are of type sigma, and we are compiling them, type closure conversion, which we did yesterday, to ET1 and ET2, right, which are of translation type. That's what the translation is. So given this, the theorem that I want to prove is that if these components, ES1 and ES2, translate to ET1 and ET2, then we want it to be the case that if under gamma s, ES1 is contextually equivalent in the source to ES2 at the type sigma, then that should imply that the translations, which under an empty delta environment, but under the translated source environment, have type sigma plus. So ET1 and ET2 should be contextually equivalent in the target language at the type sigma plus. Okay? All spelled out. The types are now there. We know what the free variables of these components are. So that's formally the theorem that we are interested in proving. You can call this the secure compilation theorem or the equivalence preservation theorem. Okay, that the translation is equivalence preserving. Okay, so let's do it. All right, so let's assume that our components translate. Let's assume that the source components are equivalent in the source. This is what we are required to show. All right? There's the definition of contextual equivalence in the target over there. All right? So what we have to do for the proof is, well, we have to start out and say, okay, let's assume that we have an arbitrary well-typed target context. And then, we can just do this in one direction. The other one will be analogous. Then let's assume that C with ET1 terminates and gives us some number n. This is going to be an integer. And then we have to show that C with ET2 terminates. Right? That's what we have to do. And we talked about this a little bit at the beginning of yesterday's first lecture, that we're going to have to end up doing some sort of a back translation from this target context to a source context. So now let's just sort of drill down into the details. What exactly is this thing that we have to back translate? What is its type? That's going to really help us out as we try to approach this. Okay, so we are assuming that we have this arbitrary, target context with, what is the type of this target context? So remember, it has to match this delta gamma and this type, right? So the whole will be whole accepts something of translation type. This is a nice context. It takes something in the whole, which is of translation type. It doesn't take arbitrary target terms. And it's promising some inputs to that term, to these terms, which are also of translation type. Okay? Remember, all the variables in this gamma S plus all have translation type. I'm going to say translation type a lot this lecture because it's really important. Okay, so, and then once we plug the hole, we expect to get a closed program of type int. And I'm writing int t, right? This is the target language. Okay, so this is the context that we're going to plug. So this is the context that we have to back translate. And I'd like to turn this sort of context back translation into sort of a term back translation. Okay? Now, I had a question yesterday from someone who pointed out that isn't the context just sort of CT? Can't we just rewrite it equivalently as this? And at the time, it was a little early, so I said, yeah, roughly that's correct. But today I want to tell you why it's not exactly correct. Okay? So if I say that I can just sort of rewrite this term to this term, well, let's note the types. What's the type of X? Sigma plus, because that's what I want to be able to put in the whole. All right? So our idea is that whenever you can take the CT and plug it with one of the ETIs, we should be able to write it instead as this. Is that our idea? Okay, this is a call by value language. Is my idea good? Okay, what's going to happen? This we know what's going to happen. First of all, let me just remind you, when I write context CT, what are the possible contexts that shapes of context that we can have in our language? Well, a context is any arbitrary expression of the language with a hole in it. And sure, we can be careful about where the values sit and where the expressions sit, but that's not even my point. The issue is that one of the possible contexts in our language, is an expression like this one, lambda x's dot c. You can put a hole right there under a lambda. So one possibility for this CT, this CT might be, I have a hole, and then it's applied to some set of values. That's a valid context. But here's another one, the one that I'm worried about, which is lambda x's with some type, and then somewhere here is the hole. That is a valid context. A context can have a hole underneath a lambda. Now, let's look at this. Are these two things equivalent? No, right? Because this is forcing us to evaluate the thing that we're sticking in the hole immediately, right? Whereas this might never even end up running it, right? Okay, so this is important. We need to be sensitive to evaluation order. We can't just expand it out and then say, oh yeah, we just need to back translate lambda terms which have type sigma plus to int, and that'll do. Okay? All right. So in order to make this explicit, there's a trick that people use when proving contextual equivalence. So contextual equivalence is horrible is precisely because you can have context of the form lambda x c when the whole, like the one that I just erased, the whole can be under a lambda. That usually makes contextual equivalence trickier to prove. And of course, there's this issue of when you're proving contextual equivalence, you're quantifying over all possible contexts. So just like, logical relations, you may have heard, are a way of proving equivalence in general. Another trick has been to use a slightly different notion of contextual equivalence that cuts down the number of contexts you have to consider. All right? And what it does is it cuts it down to, let's only consider all possible evaluation contexts. So I'll show you that in a second. And that'll make evaluation order explicit. Yes?
Yeah, I'm just a little bit confused about how you could have an evaluation context going under a lambda in a colon language, right?
Good question. So I just told you that my grammar for general context C includes, things like that. But evaluation contexts do not. If we look at the grammar for evaluation context, actually I had it up there yesterday, what is the only evaluation context in our language? It was let, right? So, of course, there's whole, target language whole, and then there is yes, very different notion of context. And evaluation context, by definition, says that the thing that you stick inside the whole has to be the thing that you evaluate next. That's where you're going to go do the work. The whole is telling you, go reduce here, and then you can proceed with whatever is in the context. That's the whole point. Okay? So lambda x dot e is not a possible evaluation context. And that's why we don't have to worry about the kind of scenario that I was just pointing out. Okay, so what I want to do is I don't want to work with contextual equivalence. I want to work with a notion of equivalence called CIU, which is about cutting down, which is about saying for all possible evaluation contexts, if I stick the terms into the evaluation context, I will get equivalent results. So let me just show you what CIU looks like. And then there are techniques, for this language we could very easily prove that contextual equivalence and the definition of CIU equivalence that I'm about to show you are actually equivalent. Okay. All right, so what is CIU? Digression. So contextual equivalence is up here. Let's define CIU equivalence for the source language first because it doesn't have a type variable environment delta. So it'll look simpler, right? So I want to say that ES1, ES2 are CIU equivalent in the source language at a type sigma. How is that defined? Well, we basically say that for all possible evaluation contexts, I'm going to need some more stuff. If I have an evaluation context that has a whole of type sigma, so evaluation contexts are a subset of general contexts. That's another thing to keep in mind. Okay, so I can write the same sort of typing derivation style for them. It's just that, there are far fewer of them. So if I have an evaluation context that takes something of type sigma. Now you'll notice I said that the whole accepts something of type sigma, but I did not put a gamma s here. Okay? That's because when something gets into a whole inside an evaluation context, it must already be closed. Think about it, right? With contextual equivalence, you can write down that context, which means that this context is providing an additional binding for terms that you can put in the whole. Okay? But an evaluation context doesn't, the grammar doesn't include this. You can't provide additional bindings. Anything that you stick into the whole of an evaluation context must be closed. It just falls out by the nature of what evaluation contexts are. All right? This will always be true in any language that you deal with. All right, so evaluation contexts necessarily have a whole that takes closed types, terms of closed type. And does it return? Well, let's just say it returns an integer. All right. Okay, so now how do we fix this gap? The term that I want to stick into the whole of this evaluation context wants some, has some free variables that need bindings. How do I provide those bindings? Yeah?
Graph substitution.
Exactly. So we just provide a substitution. So I'm going to say for all possible substitutions gamma, and this is in the source language, so everything is source. I won't put S. I need a substitution that satisfies this property. Maybe I'll put it on the other side. The other way. That's my way of saying this is a substitution that satisfies my gamma S. Let's put S's. Okay? So just find me some values to substitute for each one of the variables such that they respect the types that gamma S says they should have. Okay? All right. So I have a well-typed substitution, and it's arbitrary. I can substitute anything for all of the variables in here, as long as it's well-typed. Okay. So if I have an evaluation context and I have such a substitution, then what I want is I want to say that if I take the evaluation context E, I take my term ES1 and close it off, because it has free variables. I close it off, and then I stick it into this evaluation context E, that should produce the same value or the same number as running the other side. Both sides produce exactly the same number. Okay? So this is CIU equivalence. What we've done is we've cut down the space of evaluation context that we consider, and we'll know that we won't have evaluation order problems like before, and also we separate out what are the values being substituted in for all of the free variables in these terms. Okay? All right. I'm going to do some rewriting on the fly, and I'm going to adjust this to turn it into target CIU equivalence. By the way, what does CIU stands for? Weird, 3 letters, right? Question? Hand up? Perfect, timing. Okay, CIU stands for, literally the words are closed instantiations, and the word U stands for uses, but you should read it as uses of closed instantiations. Okay? This is due to a paper in the 90s, maybe 94, by Mason and Talcott. And basically, they're the ones who defined this sort of, definition that allows you to prove contextual equivalence, but with a much cut down set of contexts that you have to consider. Okay? So we're still quantifying overall possible evaluation contexts, but there are evaluation contexts which are far fewer than general contexts. Okay, so uses of closed instantiations. That makes sense, right? An evaluation context, when you stick something in the hole, it's going to use it immediately. That's the use part. Closed instantiations, look, we're closing off the term before we stick it in the hole. Okay? All right. So let's turn this into CIU equivalence for the target language. I need a DOM. This now has target types. So 2 target terms, ET1 and ET2, are CIU equivalent in the target. And I apologize for rewriting on the board. Sometimes people hate that. But I think they're very similar, so that's why I'm doing it. Okay, so, and these target terms have to have type tau, because that's the letter I'm using for my target types. Okay, so 2 target types are related, or are CIU equivalent, if for all possible target evaluation contexts and all possible substitutions gamma t, well, what else do I have to do here? Well, now the whole has to say that, I have to stick in terms into the whole that are closed with respect to gamma and with respect. Right, so let's start there. Okay. But if they're closed with respect to gamma and delta, all right, what does that mean? And I should change my sigma to a tau. Here's the problem. This tau might have free variables alpha in it, which are in here, right? If I'm saying that I have to stick in a term into the whole in which I've closed off all the term variables and the type variables, that means I might have substituted bool or int or something else, or int arrow int for my alpha, right? And when I do that, my substitution principle tells me that, well, I have to do the same substitution over here, right? Okay, so let's pick some types to substitute for all of the type variables in delta to start out with. I'll write little delta, which is a substitution. Think of this as a map from alphas to types, alpha 1, tau 1, etc. Okay? So pick a substitution little delta such that we normally write it like this. Satisfies that, and that should simply be read as for every single type variable in delta, you have a binding in here, and all of those types are closed. Should I write it out? Basically, it says that the domain of little delta is equal to the domain of big delta, and for all alpha in delta, it must be the case that delta of alpha is a closed type, is a valid closed type. Okay? So pick a substitution, little delta, that gives you closed types to stick in for all of those alphas. All right, so once I've picked a type substitution, that means I know that I'll have to substitute the same types into this tau to close it off. So that's what my whole has to be. Yes? Yeah, only right now I don't want you to think in, yeah, I mean, essentially, yeah. Don't think of them as existential types. They're just type variables, right? So don't specialize to the case of existentials. This holds equally well if I added universal types to my language. It's completely does. Okay? You want to think in terms of what is the shape of my judgment. There are some abstract type variables, and I need to plug in something for them, substitute something for them. But don't dwell on whether you have existential types or universal types or whatever. I mean, it's the concept of type abstraction. Okay? Okay, so the abstract types need to get turned into concrete types. That's essentially what we're doing by picking this substitution and applying it to tau. All right, so of course we still need to say we need a substitution for the term variables that are free in here, right? So let's go back and say, yes, we need so, is that right? No. Why not?
Gamma has type variables.
Gamma has type variables as well. So what we need to do is we need to close them off with delta. And then after that, we need to pick a substitution that gives us the appropriate, so if gamma t says that we need some x with type alpha to alpha, and we have picked bool for that alpha, then what it's actually now saying is that we needed something of type bool to bool. And that means that which is a Boolean to Boolean function. All right? Okay. So, so pick substitution for your type variables. Pick a substitution appropriately for your term variables. The whole in here has to have, the closed type, the concrete type. And then we simply want that E, when plugged with a closed term, and we close it off, we close off all the type variables and the term variables on both sides. And I should change all the S's to T's. Okay. Yes?
So why do you need to apply the type substitution in the evaluation context? the types start appearing in the terms somewhere?
So types are appearing in the terms somewhere. Yes, they might, right? So normally this is, I mean, it's easier to show with polymorphism rather than with existential types. So let me just do it that way. So just like in, I explained that general contexts might include that. If we had polymorphism in our language, then they might include something like that, right? This sort of binding position, alphas in a binding position, come up in unpack in our language, right? In the body of the unpack, you're dealing with expressions that have alpha free in them. So, same principle applies, but this time the alphas are being bound in the unpack. Okay, so does that make sense? Any other questions?
What does what's like the function that wraps the delta?
Oh, yes.
No, I just can't read the board.
Oh, here. Right here?
Domain, thank you.
Oh, up here, domain. Sorry, I scribbled it. Yes? Yep.
By delta first and then gamma E, Q1, and E2?
It doesn't matter either way. And the reason it doesn't matter is because we have required that this map all the variables to closed terms. And they're closed with respect to types, because we've closed all the types in here. So these don't have any free alphas. And so whether we put this here or inside, it won't matter. You can do either substitution first. Yeah. A good question. Yeah?
Why do we need domains just be
You can make...
just like capture the set of variables and any substitutions?
Yeah, so really what we need is this. Subset is fine. It's just easier if you set it up to be equality, but it doesn't matter. You must provide a binding for every single type variable that appears in delta. That's the requirement. Okay? That's CIU. And now what I'm going to do is the theorem that we're trying to prove, I'm just going to claim that it's straightforward, sort of, to prove that CIU equivalence implies contextual equivalence and contextual equivalence implies CIU equivalence. I won't show you the proof, but just trust me on that. And then, as a result, since they're equivalent concepts, I'm going to change the statement of my theorem to, I actually want to prove that contextual in source implies contextual in target, but in order to carry out the proof, I'm going to use CIU. Okay? All right. So, I'm now going to erase the CIU definition, if that's okay. Not yet. Yes?
So shouldn't be the domain of delta this morning?
Oh, it's the other way around. Yes, of course. Everything in here must be contained in here. Yeah. Right. Okay. All right. So let's go back up here. Actually, maybe I won't erase this yet. Now, in order to do a proof of CIU in the source implies CIU in the target, we have to, in order to show this, we have to assume that we are given an arbitrary evaluation context, and we are given a delta and a substitution gamma, right? Okay, so let's see how that plays out. So I'm going to say, consider arbitrary evaluation context from the target language. Its whole is what? Well, this has to be closed. But notice that our delta there is empty, right? So that means that we don't need to substitute for any type variables. Okay? So what does that end up looking like? It means that when we say consider an arbitrary evaluation context with a whole of the right type, we basically require the whole to be of that type. Since we don't have any free type variables, we don't end up substituting anything. We don't end up changing our sigma plus, right? So I don't have to put a delta outside it. Does that make sense? Or did I do it too much on the fly? I'm not getting enough nods. Delta must be empty. The little delta that we picked must be empty because the big delta is empty because of this, right? Okay, so consider any evaluation context with a whole of translation type. and a result of the type int, as before. Our delta is empty, right? So delta must be empty. I've already concluded that, so I won't even write it down. And then we have to pick a substitution gamma t that satisfies empty delta applied to this environment. In this case, it's the translation environment. So we are going to say that we have a gamma t that type checks under, gamma s plus. Okay? All right, so what just happened? We have an evaluation context that takes something of translation type in the whole and gives us back an int. All right, we have a substitution which contains a whole bunch of values to substitute for variables, but every single one of those values has to have a translation type. Okay? All right, so those are the things we're given, and now we need to assume that ET with gamma t of ET1 terminates and gives us some number, and we have to show that the other side does the same. Okay? All right, now we'll get to the interesting part. That was actually the boring part. Okay, so let's talk about what it is that we now need to back translate. What do we have as a hypothesis? We know that these two source terms are equivalent under arbitrary evaluation contexts and substitutions, right? The CIU definition for the source language. But this says that if you give me any source evaluation context and source substitution, then stuff happens. But here, what I've assumed, what I actually have in my hand right now is a target evaluation context and a target substitution. Okay? So in order to make progress on this proof, in order to use the only premise that we have available to us in this theorem, we have to take this target evaluation context and this target substitution and somehow turn them into source evaluation context and source substitution. And what's going to help us is that everything here, this substitution, contains values, target values of translation type. All right? If we pick that translation type right, we should be able to do this back translation. And that's sort of the biggest message of this, all right? What about the evaluation context? Well, the evaluation context takes things in the whole which are of translation type. And look, it returns things that are of translation type. Int t is the translation of int s, right? Okay, so even though this evaluation context on the inside, or any of the values sitting in here, right? You could have lambdas, et cetera, packages, that on the inside might contain various features that we don't have in our source. Maybe we're using tuples inside that target code. There are no tuples in the source. Maybe we're using existentials, unpacking them and dealing with them in various ways, but there are no existentials in our source language. But the idea is that even though they're on the inside, they don't produce results. At the boundaries, they only take in things of translation type and only produce things of translation type. That's what's going to save us. All right? Okay. So what we're going to try to do as I start setting up this back translation is intuitively, we're going to say, I need to back translate some kind of a term. If it has any free variables, they are all of translation type, and if it produces any outputs, they are of translation type. Okay? So if I stick to that, that means that on the inside, whatever non-translation type terms I have sitting there, I'm going to try to do some amount of partial evaluation to get rid of them. Okay? All right. That's the basic idea. All right. Let's... Okay, so just to make this crystal clear, I don't want to evaluate, back translate an evaluation context. So I'm going to sort of rewrite this and say that, if sticking ET into an evaluation context is really the same as sticking, let's say, sigma plus into ETX, that expression. This was what I had before, but I had it with general context, right? But this time, it's actually correct, because what an evaluation context does is this is the first thing it will reduce, and we are morally doing the exact same thing, right? All right. So that is why I claim that it is enough to back translate terms of this type or shape, right? So what is this term? And actually, I'm being a little honest here. My thesis is that I need to set up one back translation judgment. And it will look like, if you give me any target term that has a translation type, I should be able to back translate it, assuming that it only takes translation types as inputs. So I'm going to allow it to have free variables that are of translation type. If you give me something that has this type under and takes variable and has variables of translation type, then I should be able to set up some sort of a judgment that produces a purely sourced term. And that purely sourced term, we will then show, will always be of the type sigma, the reverse of the translation, right? Okay. This is what I want to set up, and all I've been doing so far is trying to justify that that is enough, right? So just given what's on the board right now, I'm telling you that I can take an ET, forget about these parts for a second, right? I can take an ET and rewrite it into a lambda x ET of x, right? What is the type of lambda x ET of x? Just a function. What's the type? Sigma plus. Okay. Int t is an int s plus. Okay. But is sigma plus arrow int s plus a translation type? No, it's not. Okay. But I can do a trick. If I have any term, an arbitrary term et, that has this type, then I can always say that, okay, well, you know, I can sort of move this into the context. That's all I'm trying to motivate. All right? So this actually is a lambda x with some e. Let me be a little bit more proper. Our term here has the general shape. Okay? That is not a translation type. So what I'm going to do instead is I'm going to say, yes, but if I go look at the body of this, above the line, so to speak, right, then I have to take my, oh, it's closed. So I can stick, lambda sigma plus in the environment, and now I can back translate that. That fits my invariance that I have in mind when I set this shape of back translation up. All right? So now do you believe me that it is enough for me to back translate arbitrary terms that have translation type? You have to believe me, otherwise we're doing back translation of a funny thing, and you know, it won't be useful to proving our final theorem. Yes? Did you have a question? Oh, you didn't. Oh, you were trying to decide if you believe me. Yes?
Just to make sure sigma plus is closed, right?
Sigma plus is closed. Yes, absolutely.
By the empty type. Okay.
Right there. It's coming from there. So sigma plus is a closed type, and we already know that we didn't have any type variables to contend with, which is making this easier. Yes?
What if you provide a vague, a bogus existential type, right? Like so environment alpha could be just an empty triple, and we just
So you're worrying about.
I'm saying just let's rewrite the lambda to fit that type, to fit the existential type, and just make alpha always empty tuple.
I'm saying you're worrying about that the wrong moment in time. Right now, that is technically not a concern. Something like that will become a concern shortly. So hold that thought. Right now, if you very, very formally follow the steps that I laid out for you, I claim that I have done this right, you know, in the sense that this is a lambda x ETX. the type of the thing in the whole is a translation type. The result of this expression is a translation type, right? So if I write down the derivation, the typing derivation for this term here, I end up with in a closed environment, right, because closed environment, I have a lambda x et. It is of type sigma plus arrow int plus. That means that by inversion of that lambda typing rule, this has to be sitting at the bottom, right? And this satisfies the constraints that I've laid out here. I'm trying to back translate an arbitrary target term that is of translation type, but is willing to accept inputs that are also of translation type. I'm allowing for those here. So formally, I've hopefully dotted my I's and crossed my T's. Okay? All right, good. Okay, so let's go from there. We're going to work on this. We're basically going to take every single target term that is of translation type and write down how we expect to back translate it. Okay? So let's start with the super easy cases. There are all of the terms in the language. We have to consider every single shape, right? Typing rule for every single one of them. If they are of translation type, we do a back translation. Otherwise, we don't need to. So, what's the first one? Let's do variables. Here's what I'm back translating. In an empty delta and a gamma s context, I have an xt whose type is a translation type. I need to back translate it. I know by this typing derivation that it must be the case that gamma s plus, when I look up xt in there, I get a sigma plus, right? Okay, so I want to produce a back translation that has type sigma. Let me specify one other thing. Let's not write this here. Let's write it as a where. Where's my eraser? Okay. I wish to produce ESs that have type gamma s. Notice that this is translation of gamma s. Under gamma s, I should be able to type check ES, and it should have the type sigma. Okay? So, and how am I turning my translated gamma s plus type into a gamma s? Well, I'm taking every xt that's sitting in there and turning it into an xs, just like we did yesterday. Okay? If it's a yt, I turn it into a ys. So that tells you the answer to what I want to do here, right? Take an xt and turn it into a source variable of the same name. Okay. And this will type check xs according to what I just wrote I want here. It should be fine. Because when I turn this gamma s plus into a gamma s, I'm changing the names of the type variables, and I'm changing every sigma plus in that into a sigma. Okay? All right. Rule 2. Next thing to back translate is our integers. Now, what type does n have? Does it have a translation type? Oh, good, then we have to deal with it, right? So it's an int t, which, yes, is simply the translation of an int s, right? Okay, so that means we have to back translate it. And, well, we just produced the same integer, but in the source language. That was really easy. Okay. Next. What do we have to translate next? Let's just go through our list. Done, done. Lambda x et. What's the type of lambda x et? What's the type? Tau bar to tau prime. Is tau bar to tau prime one of my translation types? Is it a translation type? No, I don't need to back translate it. Yeah, I don't have to do this rule. It's so cool. All right. All right, and I've erased the n. So what do I have to do? Well, I don't have to do this. What about tuples? Are tuples a translation type? So if I try to back translate a tuple in the same way that I was just writing down for the lambda, and I have a v1 through vn tuple, then its type is some kind of tau 1 through tau n. And is this a translation type? No. So I don't have to do this either. Good? Okay. Next. Not needed, not needed. Pack. Do I have to back translate a pack? Yes. Because a pack has an existential type, right? And that is definitely a translation type, or it could be. Okay, so but it's important to note that the kind of pack that I have to back translate must have a translation type. So it's not going to have any existential type. It's going to have an existential type that looks like this. Okay? All right. Under empty and gamma s plus, I have a pack that has a tau. I'll write this as tau just to remind you, but maybe I won't right now. I can if you want me to. So that's my pack, as exists alpha something. I won't write that part. But its must be a translation type, so let's just write it out. It has to be something like this, right? For some sigma 1 plus and some paired with alpha. Okay, so I'm back translating a package with a very particular type. Okay, now let's do this. Why should I be able to do this kind of thing? All right, we have a value here. Right. What do we know about that value? Let me start with the first question. Can that value be a variable? Or let's start with, what is the type of that value? What is the type of that value? Pack rule. Remember your pack rule from yesterday. Typing rule for pack tells us this value must have this type, but with the witness type substituted for the alphas. So here's my witness type, right? I'm going to substitute for the alphas. So this guy has to be tau comma sigma 1 plus arrow sigma 2 plus paired with a tau. And the taus are tau n's, right? I'm just going to write it because it helps my sanity. Maybe it helps yours. Okay? Just to remind ourselves. All right. So this value right here has to be a pair of a function and some tuple. Or, well, just, no, actually not a tuple. I do not know that this is a tuple. It's just some type. It could be int. It could be bool. It could be a function. Nothing here tells me that it's a tuple, even though I wrote n, which is perhaps not a good idea now. Okay, so this is a pair. Is a pair, so does V have translation type?
No.
So can V be a variable? V is sitting right here. It must type check in this environment. Let's write it down. By the pack typing rule, this must be the case, which means that V must be a pair. And if it's a pair, then it does not have a translation type because pairs or tuples are not translation types. Cool. So then what is V? All right, so you notice what just happened here? This is really cool. We have a term that only accepts the intuition, right? The intuition is that we are only back translating terms that accept inputs that are of translation type. These variables that I put over here, these are my inputs, and they have to have translation type. That means that this particular value that I'm looking at cannot be a variable because I'm not taking tuples as input, right? So that means I know, and plus it's a value. So what is the canonical form of a value of pair type? It's a pair, right? So that means, therefore, I'll write therefore here, but I don't have to. This V that I have, it must be a pair of two things. The first of which happens to be a function. So just again for our sanity, I will call it VF, and I'll call the other one VN. And this is just for reminders, right? I mean, there's nothing here which tells me that really is an environment. That's just our intuition. Okay, so, all right. Now I know that it's a pair. What do I know about the VF? What is its type? A function. A function of this type, right here, is something of that type, a variable. Is that type a translation type? Okay. So that means if this V is the pair VF, VN, then that means that this VF sitting over here, which is not a translation type, also cannot be a variable. Correct? So what is the canonical shape of this VF? Lambda? Just read off what this tells you. I'm going to write Z because I've religiously been writing Z whenever I write the environment. It just keeps it straight. Okay. All right. And the second argument? And then some body. Right? Okay, cool. All right, so we know it has to look like this. Now, what do we know about Vn? Let's just write it down. We know that under gamma S plus, Vn that's sitting over here has to have this type tau n that we know nothing about. Okay, so now, how do I proceed? Okay, so intuitively what's going on? If I'm back translating something, a package that has this translation type, which is the translation of a function type, then what I expect to produce as a result of this back translation is something of type sigma 1 arrow sigma 2, right? And what we're doing right now is trying to reconstruct that. So we've managed to find the function that's sitting inside the package. That's good. And this function takes this xt colon sigma 1 plus as an input. So I'm just going to start things off and say that when I back translate, I think I'm going to want to produce a lambda xs that takes a sigma 1 as input. And then I don't quite know what to put there yet. I don't know what the body of the function is. Because I'm doing this thing where, xt's, if this is a function that takes an environment but it takes a normal input, which is of translation type, then I want to turn it into a function which takes same variable name but in the source and something of type sigma 1. And then this squiggly part here has to produce, I have to stick in an expression there that produces something of type sigma 2. Okay, now, what do I know about this function? Well, I know that it has this type. So it takes a tau n and a sigma 1 plus as input and produces a sigma 2 plus as an output. Okay? So clearly, it's this body here that's the sigma 2 plus that I want to back translate to get a sigma 2. So let's do it. Can we do it? That body, ET, has type sigma 2 plus. In what environment?
The arguments.
The arguments. Okay. So I need to put here, and remember I want to back translate. Yeah? Okay, what are my argument types? So let me stick gamma S plus there, and then I have Z colon tau. Let me make it wider. So Z tau n and X. Do I have a problem?
Yeah.
Yeah. What? Tau n is the problem. We do not know what it is. It was abstract. It came out of the package. There's nothing that requires that this be a translation type. Normally we expect it to be a tuple, Okay, so I can't put this here without violating my very carefully set up invariant. So what do I do with it? By the way, do I have a value that has type tau n? Okay, so then maybe here's a strategy. This has a free variable z that needs a tau n. I have a value that is a tau n. Can I back translate that? these type checks, I have managed to produce a term that is of a translation type in an environment that is still sticking to my invariant that all the variables have to have translation type. I can back translate this. I can get an ES, and that ES will have the appropriate type sigma 2, and therefore I can use it to build this term that I'm trying to, my back translation in the source. Yes?
In the target language, the typing for lambdas doesn't preserve the context though, right? So why do we keep gamma S plus in the top here?
Oh, right, that's just, that's a mistake.
Okay.
In fact, I didn't have it in my notes, but as I was hurriedly writing it, I put it there. Okay, thanks. Okay. So what did we do? This rule actually shows you a lot of what is cool about, this idea of you have inputs that are of translation type and outputs that are of translation type, and in between you get to do some munging, right? And the fact that, things can't be variables is really important. And that's actually, this was my cheat. I wanted these rules to be quicker. That's why I selected a language that was already in monadic form, monadic normal form, so I could easily show you, do this kind of reasoning that if this is a value, then it can't be a variable, therefore it has to have a canonical form. In general, you have to deal with the case that, you can put an expression here, but the intuition there becomes that you essentially have to evaluate that expression. You have to do some, partial reductions inside that expression to get it down to some canonical form and then proceed from there. That's possible too, it just becomes more hairy, too hairy for a lecture in some sense. Okay, so we have done packs. That means we're done with all our values. What about if then else? Let's do that real quick. Oh, can I erase this? Or should I use a different board? Let's use a different board. Let's use a different board on that side. Okay, so I want to do, this is an easy case. I need to back translate if 0, VT, ET1, ET2, and only if it has a translation type, sigma plus. And what do we know from the typing derivation for ifs about what the type of VT is? What's the type of VT? This is if 0, so it's an int. So that's a translation type. That means I can back translate, and I can get a VS. So if it's a variable, I'll translate it to a variable. If it's a number, I'll translate it to a number. Either way, I can do that. All right. What about the ET1 and ET2? What are their types under gamma S? Both the ETIs have type. Sigma plus. So they're of translation type. That means I can back translate them too to ES1 and ES2. I'll just write ESI. All right, that means that I can produce a back translation. Now this is a source term that is if 0 VS ES1 ES2. So that was easy, right? Because every single subterm happened to be of translation type. So things worked out. Okay, what's next? Application. Okay, let's deal with application. So I have a V, I'll write F to remind me in the function position, and then a bunch of arguments, VT1 through VTN. Right, so that's application. Okay, I'm only back translating if this has a translation type. So I need to do this, right? But now let's do the same sort of case analysis that we did when we were back translating the pack. What is the type of the VF? A function type. Okay, so gamma S plus VF has type some tau 1 through right, tau 1 through tau n to some, to what? What's the result type of the function?
Sigma plus.
Sigma plus. Is this a translation type? No, functions are not a translation type. Okay, so does that mean, can VF be a variable? Okay, that means it's canonical, it has a canonical shape, right? It's a value. So what does it look like? A lambda, all right. So I'm going to write VF is some sort of a lambda that takes a bunch of xt1 through of type tau1 through xtn of type tau n and has a body, et. Okay. Now, fortunately, this body returns something of translation type, a sigma plus. I need to back translate that body somehow, right? Well, but let's talk about the arguments. What about the arguments? What are the types of the VTIs? Are they of translation type? No. Okay, so they're not of translation type. All right. So what we want to do is, well, we want to do the application. We want to take all of these arguments and substitute them in for all of the variables, and then we get a closed body for the lambda. Basically, we want to do the beta reduction, right? We get a closed body of the lambda that will have type sigma plus, and we can back translate that. So in other words, we want to say, take ET, substitute the VT1 for XT1 through VTN for XTN. That expression after the substitution must have the result type sigma plus. That is a translation type. And what environments? So we should be able to back translate that into an ES. This ES has type sigma. So that's what I produce. So remember when I said you locally do some partial evaluation? We just did that. Internally, we found internally inside this term, externally this term has a translation type, so it's going to produce something good. But internally, it's doing some work, so we just let it go ahead and do some work, right? We do some partial evaluation right there and proceed. Okay? I guess I don't need a gamma S plus here since this is target of closure conversion. So, same rule applies. Yes?
Could have three variables in them?
Oh, yeah. Yes. VTIs could have three variables in them. Yes. You're right. Okay. And what matters is if they're of translation type. Okay, so that's application. What do we have left? Projection. When should we have about 20 minutes, right? Okay, so we have projection left, projection from a tuple, unpack, and let. All right. I don't think I'm going to get through all of them, but let's get through as many as we can. Let's do projection. Do it up here. But I think you're getting the hang of this now. So I want to translate, or back translate, a tuple, projection, so pi I from a V, and I know that the result is going to be of translation. Okay? What do I know about the V? What do I know about the type of V? It's a tuple. Okay, so it has some type tau1 through tau n, tuple of tau1 through tau n. We don't know anything about that tau1 through tau n, sort of, but we do know that we're trying to project the I thing, and once we project the I thing, we get this sigma. In fact, let me just write it as a sigma I, right? So we do know from the typing rule that I has to be between 1 and n. Okay? And therefore we know that there is a sigma I in here which matches up this sigma I. Right? or rather something of type sigma I plus. One of these, the tau I in there is actually going to be equal to a sigma I plus. Okay, so what do you think we're going to do? Yeah, right, it's not of translation type, so we know that it must be a tuple of v1 through vn. And the thing that we want at the end of the day is vi out of there. And fortunately, our vi has a translation type. So we can back translate it to, let's call it a vsi. And that vsi is what we produce. So again, same principle. Do some partial evaluation. Okay. Now we're getting to the harder cases, okay? Or even harder cases. So with the let and the unpack, you kind of have to do a careful inspection, because even if an unpack produces something of translation type on the outside, this thing, if it could be of translation type or not. Right? So you have to deal with those two cases separately. And let has a similar intuition. If this is of translation type, so let's assume we're trying to back translate an entire let that produces something of translation type. If its subterm that's sitting over here does happen to have a translation type, then just go ahead, back translate the ET1 into an ES1 and produce an expression that says let XS equal ES1 in ES2, because this also has a translation type. Right? Should I write that one out? Easy. Let's just write that one out. And then from there, here. I feel like I need more erasers. Have I left my eraser somewhere? There's only one. Okay. And then the one I really want to do is unpack. But let's just... All right, so let xt equal et1 in et2 has a sigma plus. Okay, let's write it as a sigma 2 plus. What does that mean? Well, if we are dealing with the situation where et1 does have a translation type, sigma 1 plus, if, right? Then we are able to back translate it to ES1, and then we want to back translate ET2. But notice that if this has translation type, then what we have to add to our environment is some xt of type sigma 1 plus, which doesn't violate our invariant. And so now I have an ET2 that I need to back translate. Its type is sigma 2 plus, so I can back translate it to an ES2. And my whole back translation produces let XS equal ES1 in ES2. Okay? Now the harder case is where this subterm does not have a translation type, which means that you need to go in and do some partial evaluation. That case itself can, I'm not going to show you all of it. It requires care in that you want to say that the intuition still is that you want to evaluate that subterm that is not of translation type and then substitute it for the X and proceed from there. Okay? But that kind of evaluation can be tricky. If this is entirely of non-translation type, which means that it doesn't have any subterms or variables that are of translation type, then it's super easy. Just run the thing. Okay? If it does have some translation type variables sitting, or subterms or variables sitting inside of it, then you need to sort of carefully break this up into talking about an evaluation context and the shape of an evaluation context. In fact, frames of an evaluation context, and sort of drill down and say, where are the boundaries? There's some subterm in there that has a translation type, but around it there's a whole bunch of stuff that does not have translation type. How do I deal with this? Okay? I'm not going to show you that whole thing because I want to do unpack. And actually, I want to say some other things too. So let's do this rule as a sort of last rule. Unpack some alpha xt equals VT Okay, so suppose that I want to back translate that. All right. Now, let's assume, again, there are going to be cases, right? Let's assume that this actually is not a variable. Can it be a variable? Yes, it can, because it's a package, right? And that package might be of translation type. Okay? So that's one case. Let's do the other case. Suppose it's not a variable. So it's an actual pack, right? And you could do this as saying it is a pack of translation type or not, but I'll just do it as, we know that it is not a variable. So VT not var. Okay? That's the case I'm doing. Well, so if it's not a variable, that means that it has a canonical shape, because it has to have existential type, right? We do know that under gamma S plus, this VT must have some kind of an existential type, which means that it must be of the shape. Since it's not a variable, we know that VT must be a pack of some type tau. Let's call it tau prime and B prime. Okay? So if we actually now have the pack, we can just sort of do the unpack and the substitution and continue from there. So what we can do is basically go ahead and substitute for the alpha and the xt that are free in this ET. Okay? So I'm going to take ET, I'm going to substitute my type tau prime for the alpha and V prime for the xt that has translation type. So I back translate, I get an ES, the whole thing gives me an ES. Okay? All right. Okay. All right, yes. So now let me sort of wrap up, because tomorrow I want to cover other things. By wrap up, I mean like I need 10, 15 more minutes. We started at 10:50, right? Okay, so, here's where I want few things that I want to point out. So the whole thing that I've shown you is a technique that in the literature is now being called back translation by partial evaluation. All right? If you want to understand the details of all of this, here's a reference. We have a paper called Non-Interference for Free. It was for, that is a equivalence preservation result for a language that's essentially a security typed language called the dependency core calculus down to a polymorphic language. But it uses a back translation technique that is very much like this one. All right? So if you ever find yourself using this technique, and by the way, the other thing to say is that this kind of back translation technique only works for languages that are terminating. All right? And let me say that, and then I'll get to the part where I talk about how we do this for non-terminating. Anyway, so this paper, Non-Interference for Free, this is William Bowman, my student, and myself, and this was at ICFP 15. It's on my webpage. I can put up links on the lecture page as well. So that has all the gory details with all of the case analysis. After you have defined this back translation, there are two things that you have to do. Number one, you have to show that the back translation is well-founded. Because look, we're doing a lot of partial evaluation, all inside, right? We're sometimes just substituting what looks like bigger terms for, like substitution might end up growing our expression temporarily, right? So we have to prove that the back translation is well-founded, right? So the first thing we prove is that if anytime you have an ET that is of type sigma plus, then there exists some ES such that you are able to back translate and actually produce it. Oops. This should be ET. Okay? Read that as back translation exists. Okay? And then I keep using the word back translation to say that, I'm taking target things of translation type and turning them into source terms of the original source type. Okay. But I also need to prove, because I want to use this in my overall proof up there. So what I'm really after is trying to back translate this to a semantically equivalent term. Right? So after I've done the back translation and shown that it exists, I also have to show that if I am able to back translate some ET of type sigma plus to some ES, okay, then this ET and this ES are semantically equivalent. And how are we going to state that? The logical relation from yesterday, right? That exact same one. So we are going to prove that in the environment gamma S, this ES that we just produced, which has type sigma, is cross-language related to the ET that we started out with. And remember, we put sigma there, which means that ET has type sigma plus. So the exact same logical relation from yesterday. You use that to prove that the back translation is semantics preserving. Okay? All right. And once you have those pieces, then you could essentially come back here. You can say that you are able to back translate this to something semantically equivalent, which means that, plus by compiler correctness, you know that your ESIs and your ETIs are already semantically equivalent. So that means you're taking semantically equivalent things and sticking them into semantically equivalent things across, right? So you can say that if ET with ET1 in it terminates, then the ES, essentially the back translated evaluation context with the original ES1 in it must also terminate. You kind of go up, right? You go from here to, how do I do this? Then that should imply that this result of back translation, which I'm just going to write as ES, with ES1 produces the appropriate source expression, and then equivalent to the other side, you know that that has to produce the same number, and then you come down from there, and you get that ET with ET2. Oh, of course. Oh, you also have to translate the gamma. Sorry, I forgot about that. But every value that's sitting in the substitution, gamma, has translation type. So you also have to back translate that. So let me just amend this. Assume that that terminates. You've back translated gamma T to gamma S, which is semantically equivalent by these theorems, and so on. And then you complete the diagram. Okay? Bit fast, but okay? All right. Okay, so this is how we do proofs for terminating languages with this idea of partial evaluation, because that's, since we're doing partial evaluation, we need to show that they're well-founded. If you're trying to do this for a language which has recursive types or recursion or something like that, then you won't be able to show that back translation by partial evaluation is well-founded. Okay, so there are, the community has developed other techniques. There are techniques in the literature that you use for Turing-complete languages. And I just want to point you to a few papers so that you have the reference, and just say a few words on what roughly those results are. So, empty board. Okay. So, if your language, so let me give you another reference. We have a paper called Fully Abstract Compilation by Universal Embedding. So I'm just giving you some references so you have something to look at if you want to find out more. What this paper does is it considers a source language that has recursive types, okay, and sums and pairs and whatever else, but otherwise is very much like the source language we've been considering today, but it also has recursive types. It does a closure conversion pass, very much like I've shown you today, to a target language that also has recursive types, But in addition to that, we have exceptions. That's when life gets really interesting. When you have exceptions, you can't just use this target type system to ensure secure linking. And in fact, we end up using a modal type system at the target, which is able to say that some expression, so expressions in that type system or computations in that type system, will normally have a type written like this, which says that E is a computation that if it raises an exception, it will raise an exception of type tau xn. If it normally returns, then it will give me back a value of type tau. But then when you look at, the type system is structured to very carefully keep, these exceptional effects, if you will, separate from normal control flow of the program. Okay? And the idea then is to go from this source language with recursive types to the target language with recursive types and exceptions, but use a translation where every source expression of type sigma, when you translate it, when you do the typed closure conversion, you give it the type E void. What does that do? It says, I translated from the source. Source doesn't know anything about exceptions. This expression, whatever its translation is, sorry, I didn't write the ET. Okay, whatever its translation is, will never throw an exception, right? If your exceptional type is void, then it's an empty type. You cannot raise an exception. So what this type system is doing is it's allowing you to track expressions that cannot, sort of result in an expression being thrown. Now, internally, that expression could totally throw exceptions, but they will be handled. All right? So by the time you get to the result, the final result of something of this type, you know that there is no expression sort of crossing the boundary, if you will, right? Coming out as a result. So what this gives you is, once you use this kind of a type translation, what this gives you is, you're able to say that when I compile functions or code from my source into the target, and that accepts some input, even if that input is a computation, is a function of some sort, I am only going to link with that if that other code has the property that it might internally throw exceptions, but it must handle them. So no exception will ever flow across the boundary from that code that I link with into my compiled code, because my compiled code doesn't know how to handle exceptions. Okay? We can actually break equivalence. If you want to see, I can show you an example where equivalence breaks. But maybe in the interest of time, I won't. Does anyone want to see that? Yeah? Okay, all right. I'm getting some nods. Okay, so the example is, suppose that I have two expressions, E1 and E2. So ES1 is an expression of the form, take a function and apply it to F1, then apply it to F2, and just return unit. Okay, an empty tuple. Right? And I'll construct another one. ES2 is something that takes a function. We first apply F to 2, then we apply it to 1, and then we return unit. In the source language that I've shown you, even if I added recursive types to that language, these two would always be contextually equivalent. Because basically, even if you have recursion in your language, what could this function do? It could diverge. Right? Can't really do anything else. So I call it with 1. Okay, if it diverges here, then it's going to diverge here too, which means that the results will look the same. Right? In a non-terminating language, it's even easier. F is guaranteed to terminate, so you call it with 1, you call it with 2, but you don't care what that produces, and then you just return unit in both cases. So these are contextually equivalent in the source. But in a target language where you have exceptions, you can tell the difference between them. All right? And here's a context that I can use to tell the difference between them. A context which says catch something. All right, so what I want to do is basically pass in, I get to pass in, I'm the attacker context, right? I get to pass in a function of my choice. And what I'm going to pass in is a function that raises an exception. Okay? So this is going to get passed in for my F, which means what? And then let's say catch y equals that in, just y. Okay. Now, let's run C with I'll just say with ES1. Same thing happens if you have the closures, but, and let's run it with ES2. What answers do you get? So if I put ES1 in this context, I get 1. Because 1 got passed into this function and it got raised. All right, the second one? 2, because 2 happened first. So in a language with exceptions, you can tell the difference. You can break, if you sort of naively compile, you can break equivalence, right, in the target language, if your target language has exceptions. That's the essential idea. All right, but notice that what's happening is we have flowing into our code across the boundary some code that raises an unhandled exception. So by using that kind of a type translation, I'm basically saying you are not allowed to pass me functions that as they're, when they compute, they basically, I have a requirement that any function that you pass to me must have type E0, in this case, let's say int. So you can only pass me this function if it happens to have a body that will not raise an exception. So this one does not qualify. This does not type check. So you can't pass it to me. I won't link with it. And that's how you get equivalence preserving compilation in that context. Okay, and now the other thing was, you cannot do partial back translation by partial evaluation in a language with recursive types. So the trick there was how are you going to do the back translation? Well, the trick there became that essentially it's this. If you have recursive types in your source language, roughly speaking, you can write an interpreter for the target in your source. The actual details are not exactly that, but they're inspired by that intuition. Okay, so the idea is that we still need to be able to back translate an arbitrary term of translation type for whatever translation type in that paper. But since we can't just back translate it, what we do is instead we kind of back translate it into a universal type. A universal type is basically a big recursive sum. So think of it as the type dynamic. So we write U, and you can encode, you can write, do something like alpha arrow alpha. Every single type that can exist in the target is given a position in this sum so that you can keep it tagged and separate. So you're essentially taking a typed value from the target and encoding it as an untyped or dynamically typed value in the source. Once you do this embedding, you still have to, this universal embedding, you still have to now take the untyped back translated terms, and they have to interact with appropriate source terms. Like maybe you have a sigma 1 or a sigma 2 here that wants to interact with it. But the idea is that because they were coming from things of translation type, they should semantically be back translatable. That's the essence. And therefore, when you interact, across this dynamic and static boundary, nothing ever goes wrong. You don't raise errors, right? But you have to show this properly, basically by saying that you can have an embedding from, that there are these reverse functions that can take things of type sigma and embed them into something appropriate in this universal type. Embed. And you are able to project out without error from the appropriate bit of the recursive type into the corresponding sigma, if that makes sense. Okay? So it's a lot more work. Proving secure compilation is hard. And a lot of these proof techniques are fairly recent. Like I'm telling you about a paper that was at ICFP 16. There's another very nice paper at POPL 16, which by Dominic De Vrezi, Marco Petrignani. It is called Back Translation by Full Abstraction by Approximate Back Translation. I think. Fully abstract compilation, I think, by back trans. Okay, so this one is De Vrezi et al. POPL 16. What they were trying to do is interesting. They said, we don't even want to give ourselves the luxury of recursive types in our source. We only have recursive functions. And we want to take a simply typed lambda calculus with recursive functions and translate it to an untyped language. So this is an example of dynamically enforced secure compilation, because they had to take code from the source, and they were essentially doing an identity embedding, but they had to wrap the code with monitors or dynamic checks at the boundary to keep it safe from untyped target code. Okay? But now the issue is that if your source is, it's less rich than the one that I was talking about for this paper. It doesn't have recursive types. It only has recursive functions. You have less power to encode target things in source things. You can't just do sort of this interpreter idea exactly. So they use an idea called approximate back translation. So it's a very nice paper. And it basically relies on this beautiful insight that any target context, when it interacts with a translated term, there's only so much interaction that can happen, right? There's a sort of approximate limit that we care about, and it depends on, well, if this thing terminates and takes a certain number of steps, let's write k, all right? Then k is sort of that upper approximate behavior bound. That's just how much behavior I need to back translate. I don't need the full behavior of that context CT to be back translated. I just need enough of an approximation. Okay, I'll leave that bit at that. But it's really a very neat result. What else do I have? I have mostly talked about statically enforced secure compilation, but I want to give you one more reference to dynamically enforced secure compilation. This is a paper by Marco Piccignani and a whole bunch of other authors. It now has a very nice long journal paper, journal version, and it's called Secure Compilation to Protected Module Architectures. Okay, and this is a TOPLUS 2015 paper, and let's just look for Patrignani. Okay, so this uses exclusively dynamic enforcement from a tiny object-based kind of language down to essentially hardware, the techniques that you use in order to prove the back translation correct are going to be a bit different, which was one of the questions that I got yesterday. So that's sort of the space of really hefty results proving back translation. Actually, there are others, but they sort of predate these. And one thing that I want to say about secure compilation is that we used to live in a world where, remember yesterday I said there were a lot of results in the literature that were trying to show that some translation preserves equivalence or is fully abstract, but often they would take some target feature and just add it to the source. Because then you have a source and target language that are sort of equal expressive power, so you can do the back translation. The difficulty is that for realistic compilers, you're never going to be living in that world. You will always have source languages which have much less expressive power than the target languages that they compile to. You want to be able to jump in assembly, for instance, but not in a source language. So if you look at the history of the work in this area, initially people just sort of started out with, okay, I have rich languages, but maybe they are of equal expressive power. So there are a couple of results. The very first paper that showed that Inamide et al.'s type closure conversion actually was equivalence preserving was a paper that I and Matthias Blume had at ICFP 08. But we picked a source language that was polymorphic, had existential types and recursive types. And the target language had all of those features as well. Even then, it was a lot of work because we had to sort of take things of type tau plus, translation type, and turn them into things of type tau. So there was still a lot of work there, but we hadn't even hit the hard problem yet of how do we do this if our target language genuinely has features that I cannot express in the source, which is what I was trying to show you today. And then there was another paper at POPL 13, which is called Fully Abstract Compilation to JavaScript. Is Nick here? He's one of the authors of that paper. So this also does a similar quality kind of trick, in the sense that their source language and their target language are also equally expressive. But still, there's a lot of work to be done to show that the back and forth translations actually work, right? right? That you're able to take things of translation type and turn them properly into things of the original source type. So from there, we went to, people looking at terminating languages, like I've shown you for this lecture, and trying to ask, okay, they're both terminating, so at least that's good, but my target has some features that the source does not. How do I do this? That led to partial, back translation by partial evaluation, and that it's only like in 2016 that we have techniques that actually work for, Turing complete languages. And really the final word about this is, these results are hard to prove if the gap between your source and your target is greater. That's roughly the intuition. If your target language is able to express a lot more, you need to come up with appropriate tricks to encode that, in a sense, in your source, so that you can sort of show that a back translation exists. And that, really means that whatever result you do try to tackle often ends up being very specific to the source and target, and very dependent on that gap between source and target. Okay? All right, so I'm going to stop there so we can all get lunch. Sorry, I've gone over. But tomorrow I will do a survey on sort of, I'll talk about some more work in the space of secure compilation, and I'll talk about compositional compiler correctness, because there are a lot of sort of genuinely big questions there, and I'll do a survey of the work in that area.